Howdy AP Chemistry, we're here to talk about periodic trends. There's going to be three of them. The first one we're going to look at is ionization energy. It is the energy required to move one electron. Now the opposite of this is going to be electron affinity, which is the energy released in adding one electron. And the last one is going to be atomic radius. And just like what it sounds, it's the relative size of a stable atom. So not an ion, that would be ionic radius. We're talking about atomic radius. So the first one is ionization energy. And like I said, the definition is up here. But if we wrote it in an equation, we would have the stable atom on the left, and then we would have its ion on the right. Since we removed an electron, it would be a positive ion with the electron written out on the side. It's a measure of how much work it is to remove an electron, or how tightly the electron is held by the actual nucleus, or by those protons. Remember, the protons are attracting those electrons. And the units are usually kilojoules per mole. Ionization energy depends on two things. It depends on the nuclear charge. That would be how many protons there are, and also the average distance of the electron from the nucleus, so how far away from the nucleus it is. The lowest energy valence electrons are the first to be removed. Successive electrons take much more energy to remove because the atom now has a positive charge. So once that first electron is pulled away, it now has more protons than electrons, so now they're going to be holding on to those electrons much more tightly. So that second ionization energy is always going to be higher. The ionization energy takes a very large jump when going from a valence electron to a core electron. That would be once you pass one of the noble gases, whenever we start taking off another shell. The second ionization energy of sodium is much higher than the first, because at that point, if we pulled one electron away from sodium, we would be at a noble gas configuration, and that's why. The third ionization energy of magnesium is much higher than that of the first and the second. That's because if we pulled two electrons away from magnesium, we would have a noble gas configuration again. So that's why the third one there's a big jump on the third one. Core electrons are much more tightly held than valence electrons. So here's a good representation of that. We have the period 3 elements, and notice there's 1, 2, 3, 4, 5, 6, 7, 8 of them. Sodium is the alkali metal, and then argon is its noble gas. And notice that sodium, there's a very big jump between the first ionization energy to the second one. Magnesium, there's also a very big jump from the second to the third, and then you notice it keeps on going that way. Now once we get to its halogen right here, it's very hard to pull away any electrons, because as you may remember, it's much more easier for chlorine to just add an electron rather than just pull all the 7 electrons away from its valence electron shell. So that's why the energies are so much higher once you get down to the bottom. The big thing to remember is there's just this little staircase, usually right here, and that's where we get the noble gas configuration. The first ionization energy generally increases going from left to right across a period because of the increasing nuclear charge. And then it decreases going down a group because the electrons being removed are farther from the nucleus. And that has to do with shielding. So if we look at this, the element that would probably have the most ionization energy would be fluorine. That's not because that's in the top right. If you excluded the noble gases, because we like to omit those since they are very non-reactive anyway. So fluorine is where you're going to look. Just remember that fluorine has the highest ionization energy if you have to kind of compare those. Now there are a lot of exceptions to this, and they occur at group 3 and they occur at group 6. That's because of the shielding with the p electrons, and I'll explain on this in just a second. Actually, I'll explain on it right now. So if we try to draw out the orbital diagram for this, if we were drawing just the second period, we did the 2s, and let's do the 2p. I know it's a little messy, but we'll stick with it. And then we got 2p. Alright, so let's just do boron right here. So boron's going to have 1 and then 2. It's going to have 2 s electrons, and it's going to have 1 p. So this is going to be in group 3 for boron. This is boron. Now it's going to be able to remove this 1 electron right here pretty easily, but now we've got kind of a full sublevel right here, so it's actually a little hard to actually pull this off. Now if we took this away and then we did our next one, which is carbon, the one after boron, has 1 more electron. See, now if we were able to, well, we could pull this 1 electron away, and this, if we removed 1 electron, that's no big deal. But then if we pulled another electron, that would be the second ionization energy. Now we have a full sublevel right there. So that atoms with low ionization, or the first low ionization energy, that's what this 1 right here means, is the first ionization energy. They tend to form cations during reactions, whereas those with a high first ionization energy tend to form anions. Of course, except for the noble gases, because they're already pretty happy to begin with. So this really helps you out right here. If these are the first two elements, hydrogen and helium. Helium's a noble gas, so it has a very high ionization energy, and they're just s orbitals, so there's no big exception here. Now once we get to lithium, it has it has an s orbital, and then we get to beryllium. Now there's a decrease in ionization energy when we get to boron. Okay, alright. So there's a decrease between group 2 and group 3. So it does not increase completely across the period. We get a slight decrease between group 2 and group 3, and we get a slight decrease between group 5 and group 6. Alright? We see the same thing in the next period. We see a decrease between group 2 and group 3, and then we see a decrease between group 5 and group 6. Very small decrease, but it does matter. When we get to here, these are all the d electrons, and then we see the same kind of pattern, and then all the d electrons in the same kind of pattern over here. It gets a little wishy-washy because of that shielding, and we start getting farther and farther away from the nucleus, so it stops making a difference. Here's another representation of it with some numbers that may help you. Again, the first period it has a normal trend because it just has the s sublevel. In the second one, we have the s sublevels. We have 899, and then it decreases to 800, and then it increases again, and then decreases slightly, and then increases again. So we get the same type of pattern. It decreases from group 2 to group 3, and also decreases from group 5 to group 6. So when you get to the test, you need to remember this part right here. If they ask you about a periodic trend or why this is happening, just saying that it increases going from left to right or up and down will give you absolutely no credit. Okay? Same on my test. You need to actually state the reasons. Okay? So you need to remember why it happens, and that happens because of shielding. And it also happens because of the change in the orbitals. Okay? Also, if you are given 2 elements or 2 ions and you're asked to compare them, you must discuss both of them. Okay? If you just say This one has a higher ionization energy, and you leave it at that, you will get no credit. Okay, or you may get partial credit. You need to discuss both of them. You need to actually physically name both of them. The next trend we're talking about will go much faster because we're just talking about the exact opposite process. Electron affinity. It's going to be the addition of the electrons. So now whenever we look at the chemical equation, we have the stable atom on the left plus the electron, and we get a negative ion. The addition is exothermic. My wife is making me laugh. So if the addition is exothermic, electron affinity is negative. The more negative, the greater amount of energy is released, because remember, if it's negative, the energy is released. If going down a group, electron affinity generally becomes more positive because the electron is farther from the nucleus. There are many exceptions in that electron affinity generally becomes more negative going across a period. So as we look at this and we try to get a sense of it, notice that there are no noble gases because they just do not attract any electrons, and they're very happy. So we just have the first ones right here, and then we also leave off the group 2s. But it gets more negative as we go down, as we go across the period, and then it gets more negative as we go, and then it increases, and then it gets more negative. Now we also see a slight jump between here and here, and it does trend down as we go. Now to remember with this, the one that has the most electron affinity is going to be fluorine. Again, remember floozy fluorine, she wants all the electrons, so that's just the best way to think of that. The fluorine is in the top right, and it is also the most electronegative, so yeah, that's a good way to remember it. Now think about atomic radius. That would be the actual radius of the atom, right? Except whenever they measure this, they measure 2 atoms together. And then they, because it's very hard to actually just look at one atom, they measure the radius of 2 atoms, and then just divide by 2. So that's how it's taken. It will decrease going from left to right across the period, and then it increases going down a group because of the larger orbitals. As you add more electrons to the outside, it will increase. The best way to remember it is something a little bit like this. As we go down, we will increase and get much, much larger. Now, if you think down here, there's one lower than cesium, and that is francium, Fr. So think about Big Francis. She's the biggest one there. So Big Francis is the largest atom on the periodic table. Now, I know what you're saying, Mr. Russell, why, since we're adding electrons right here, why doesn't it increase? Why isn't it not getting larger since we're adding electrons? Well, I'm glad you asked that. Well, since we are also adding protons, right? And those protons are going to attract to those electrons because they're opposite charges. Since they attract more, the nucleus will attract them much greater, so in a much greater force. So these will be the smallest, and the alkali metals will be the largest. This slide sums up the whole thing in a pretty good picture. Just try to remember this. Remember that we have atomic radius down here. We have Big Francis down here in the corner. And then the ionization energy and electron affinity, we have fluorine over here on the right. We pretty much exclude the noble gases whenever we look at these trends. So we just want to look at the representative elements. So this is fluorine over here in this corner. So she's got the highest ionization energy and the highest electron affinity. Also, the metallic character could be a question that you have, and that also points down to francium. If you keep those reference points, that's a great way to remember. Alright, thanks for watching, y'all.